Well, thanks for sticking around until the end of the day, especially given that you heard from me this morning, and hopefully you enjoyed it enough to come back. So today we're going to be talking about how Honeycomb built our real-time observability database on top of serverless and the ARM64 processor architecture. So today we're going to talk about 4 different topics. We're going to talk first about how serverless is helpful and helps us get past some of the constraints that we would have encountered with just using on-demand servers. Secondly, we'll talk about how things can get a little bit painful when you start pushing the limits of your serverless platform. Third, we'll talk about how to do experiments with serverless and with ARM processors in your environment. And then fourth, we'll talk about how to deploy those services in production and at larger scale. So first of all, let's talk about why we might use a service like AWS Lambda. But before that, I think let's back up a step and talk about how this impacts real end users, because that's why we're here, right? Like, we're here not to use the fanciest new technology. We're here because we are trying to solve real problems. So we'd like to optimize our custom data stored retriever that we built in-house at Honeycomb to handle observability data. And here's a retriever. This is my golden retriever, in fact, half golden retriever, half Samiad, extremely cute. But that's not actually the particular kind of retriever we're talking about here. We're talking about a data retriever, not a dog that retrieves balls. So retriever here is a distributed column store that allows for real-time event aggregation and data analysis. And really, who is it for? Right? Like, the point is it does real-time event aggregation in order to interactively query over millions or potentially hundreds of millions of distinct traces. My name is Liz. I'm the field CTO at Honeycomb. I've been with Honeycomb for 4.5 years, and before that, I worked as a site reliability engineer at Google. So what's Honeycomb designed for? So our goal is to help customers who are software developers understand what in the heck their software is doing. And in order to do that, we want to make it ergonomic and fast and cheap for our customers to query their own telemetry. So I covered this a little bit this morning, but the difference between monitoring and observability boils down to monitoring is about known and knowns. It's about how do we measure things that are predictable in advance that we know in advance might fail. Whereas observability is more suited to the unknown unknowns, things that we couldn't predict in advance we knew were going to fail, but now that they're broken, we need to be able to fix them as quickly as possible. So it's basically about what do you want to see right now, and how can we make it very fast, even if you didn't tell us what questions you were going to ask in advance. So basically, this is what our UI looks like. Again, this is not a Honeycomb sales pitch. This is more of a how quickly you expect to see results when you're using an observability tool, which is, in general, if that spinning wheel is spinning more than about 5 seconds, then something has gone wrong on our back end, or you're asking something really, really complicated of us. And the point of this is to enable you to iteratively ask questions, to kind of not feel like I have to get my query exactly right or else it'll never work. But instead, you can kind of write a partial query and then to have the query complete and then to run another query based off of what you find. So it's kind of being in conversation with your code. So at the end of the day, what we're trying to do essentially is we're trying to aggregate data that we've received from your services at runtime and quickly give you the results. So this means that we have to be able to query any combination of data fields, potentially, billions of rows, potentially hundreds or thousands of different individual fields or columns, and potentially millions, trillions, right? Like, as many different possible cardinal values within each attribute. So in a nutshell, people might generate this kind of data with a standard called OpenTelemetry, which basically allows you to take traces from your application data and send them to any sink, regardless of whether it's your cloud vendor, whether it's a particular observability vendor. And then how your observability vendor implements that may depend based off of who they are. In our particular case, the way that we like to think about this data is that we decompose the data. Instead of storing it row by row, we break it up by each column, by each attribute name, and that way we store all of the attributes together, and it lets us very efficiently query the subset of data that we're most interested in. And the emphasis here is interactive, right? Like, that when you have 100 milliseconds, right, that's fast. That is faster than you can blink. When it's about 1,000 milliseconds, that's, okay, I'm taking my mug of coffee, I'm taking a sip. But if it starts taking, 100 seconds, that's at the point where I'm no longer taking a sip of my coffee. That's okay, this is going to take a while. Maybe I should get up and stretch and go make a new pot of coffee, right? Like that's no good. That interrupts your state of cognitive flow. We want you to stay in your state of cognitive flow, especially if it's 3 a.m. and you're debugging an issue. So under the hood, the way that we implement this is we implement this using a streamed data ingest that flows through Kafka. And then we wind up unpacking that data into the constituent columns, storing all of the columns associated with a given data set together, and then we upload it to a cloud storage like AWS S3. And then when it comes time to read it, we need to scoop that back off and query it and return the results. So this is great in principle, but how does that actually work, and how did we arrive at that architecture? Well, we might want to ingest potentially millions of events per second from our customers, and magic happens, and then customers can query it, right? So one way of handling this as you scale up the number of users is to scatter your users' data across multiple partitions. There's not one retriever, it's multiple retrievers. And for each retriever, there's actually a mirror of it or a pair so that we don't wind up with unavailable data in the event that we have to restart things in order to do maintenance. So these retrievers, let's suppose that they're writing all to local disk. What happens if that local disk fills up? Well, you might have to delete the data off of the local disk if you're running out of space, but that's really suboptimal because it turns out our customers like to query data that's more than a few hours old. People might, want to ask for a day of data or a week of data or even 2 months of data. So what's our solution there? Well, our solution there is to break things up to have one file per column, and then we wind up touching the data that we need, and if we don't need the particular data, we don't read it. And we also can start to think about sharding the data, because it turns out that when we have that problem of how to expire the oldest data, well, the easiest way to handle that is to break up the data into chunks by timestamp that it contains, as well as keeping track of when we received each chunk. Now, each chunk has a start and an end time, and that enables us to say, if you're looking at things in this particular 1 hour window, I only have to scan the data that has a start or end time that overlaps with that window. So once we have these kind of overlapping time ranges, so this is kind of doing a breakdown per retriever, per individual host, then we kind of have this idea of being able to expire the data and of being able to run queries against subsets of the data. And keep in mind that when I'm running a query against any one time slice, I also am running a query only against the specific columns that I want to read. So once we do that indexing, we get efficient querying, and that lets us essentially answer any arbitrary question. It's trading off, many other data stores will wind up trading off write time optimization, so they will pre-aggregate the data. So if you've ever used a metric store before, right, like it asks you to break down in advance and to say, I want a time series by machine, or I want a time series by data center, or I want a time series by build ID. But it won't let you undo that packing. Whereas storing the data in raw form enables you to do that kind of aggregation at read time rather than write time. It just potentially creates some of these complications, as we've seen, because we have to store all of the data raw, and then we have to analyze it at read time. So as we get more customers, one answer to this is to say, okay, we're going to run more than one retriever. We're going to start sharding the data. Maybe one customer's data goes to retrievers 1 and 5. The other customer's data goes to retrievers 6 and 9. And that works okay. And we can also start thinking about sharding more often and more aggressively so that we're not deleting, an hour or two of data at a time, but we're deleting maybe 10 minutes of data at a time. But wouldn't it be better if we didn't have to delete it at all? So at that point, we have introduced the idea of tiering older data to S3, data that is not currently actively being written. And it turns out, fun fact, you would think that this would make our data store slower to have the latency of going out to S3, as opposed to reading off of the local disk. But when you're reading a sufficiently large amount of data, it turns out that accessing any amount of data in serial off of a local SSD is going to be much slower than reading that same corresponding amount of data massively in parallel off of a distributed file store like S3. So yay, now we can keep data for a fixed time range, like 60 days, rather than only keeping 2 or 3 hours of data on our local disk. Huzzah! But there's a slight problem here, which is I alluded to the fact that reading data in parallel from S3 is faster than reading in serial from local disk. But if you have only a fixed amount of compute, then you are bound to have to serially grovel through that data, fetch it back from S3 in order to query it. And that could get a little bit slow. So how can we cope with this? Well, one way of dealing with this is to say, okay, we don't want the time to scale linearly with the amount of data that we're scanning. What if I could just magically add more CPU? Ooh. So this is a very on-demand bursty model. So this is my dog Flurry, and Flurry says, I would love to have lots more compute to play with, but only if I want to play. If not, if I'm bored and I want to wander off somewhere else, I don't need all of that compute. So where can we get a source of such magical compute that we can spin up on demand within milliseconds, and that we can say, hey, cloud provider, I'm done using this. You can recycle it and give it to someone else. So enter AWS Lambda, because we're on the AWS ecosystem, although you can do the same thing with Google Cloud Functions and so forth. So Amazon has kindly given us access to tens of thousands of query workers on demand, which is really, really fantastic because it means that we can just have a user query come in and we can scan tens of thousands of these individual files or columns, these files or segments at once. And that enables us to, no matter how much data the user is asking for, spin up the appropriate amount of compute to return them an answer in less than 10 seconds. So now, instead of fanning out the data across only one retriever, we're getting to have the ability to have sublinear query time by just adding more parallelism. And this works because S3 is storing the data massively parallel as well, and they're therefore able to read the data and run these read time filters and aggregations. So by buying compute in 1 millisecond units. Again, thank you, Amazon. Amazon used to bill us in the 100 millisecond increments, but it turns out Amazon will now bill you in 1 millisecond increments. So that means that if you have very short queries, it's actually feasible to use Lambda for this as well. So why would we make this trade-off? It's because developer time is expensive, because speed is a feature, right? We are willing to spend a considerable amount of money on AWS Lambda, as long as it delivers superior performance for our customers. So this means that we can get results like 50 millisecond query time, 50 millisecond cold starts. We can get 90% of our queries to return in less than 2.5 seconds. And that's, when you account for the fact that per CPU second, Lambda is about 3 to 4 times more expensive than EC2. Except we don't have to pay to run tens of thousands of EC2 nodes full out continuously, right? The EC2 startup time would be, on the order of 2 or 3 minutes from the time we requested a VM to getting one fully running. But by paying only for kind of that 50 millisecond startup time and then the amount of time to run the workers, it means that we're able to much more economically brute force these queries rather than wait forever for an EC2 instance to spin up. And that makes it well worth the cost for us to use serverless functions as this backend for filtering through our files on blob storage. And this is this architectural decision has served us really well at Honeycomb. So at the end of 2022, we were ingesting about 10 times as much data as we were 3 years prior in 2019. And we also had customers querying us, whether manually or on an automated basis, about 10 times as much. And by collaborating with Amazon and making sure that we are on the same page about capacity planning, we have been able to serve this need without any performance degradation. So here's a little bit of a caveat. Why did I say in collaboration with Amazon? The answer is because Lambda is marketed as a solution that is low code, that's no infrastructure, that you can use to very quickly get API request workers, that you can use to do tiny microservices, right? it's not necessarily been marketed for, or kind of at least with the default rate limits designed for a use case like this, where you're using it, tens of thousands of workers for 100 milliseconds or 2 seconds, and then you drop down to 0. So that's why I put that asterisk about scaling up effectively. This is possible, but you also need to work with your serverless function vendor, because they may not necessarily have designed around you in their default quotas. So let's start by talking about the scaling properties. So there's a concurrency limit that every AWS Lambda function has, and there's also a concurrency limit per account. And the concurrency limit per account limits the maximum total throughput of all of your Lambdas. And there's also that burst limit that's per function, and the more you continuously run your function flat out, the more that Amazon or your cloud vendor is going to scale that out is going to depend upon how much you consistently use that concurrency, so that they know to keep those worker nodes running, right? It doesn't make sense for them to keep you running on 100,000 different nodes if you're only sporadically using the service, because then they're paying to kind of keep your nodes pre-warmed and in memory rather than shutting them all the way down. So if you exceed your burst limit temporarily, instead of letting you invoke the function, it's going to return a 429, which tells you to slow down. But for a workload like ours that's really bursty, where you're running for maybe 3 to 5 seconds at a time at tens of thousands of concurrency, and then you're dropping a 0, and then you're running tens of thousands of concurrency and dropping a 0, you never wind up hitting that burst scaling threshold until your query is already finished. So by looking at what the actual concurrency was that we are demanding from Amazon, and then working with their capacity planning teams, we were able to negotiate with them on raising some of these limits so that we could scale a little bit faster out of the gate, because they knew that our workload was going to be worthwhile for them to keep warm started rather than starting from cold every time, and that we would always, maybe not come back every single second, but we would definitely come back, multiple times per minute at least, and therefore make it so that it was worth keeping our workers in memory. So study your limits and change your retry parameters at least to, don't ignore a 429 failure. It's not a permanent failure. It's just I couldn't run that right now. Retry it, and eventually you'll get through. And when you have adequate observability, that gives you the data to go to your account reps and say, this is why I need a quota increase. I know what I'm doing, and I promise I'm going to collaborate with you. All right, let's talk about the median startup time. You'll notice why I said median. Why did I say median? Well, it turns out that, sure, you can get cold starts in about 30 milliseconds, but there is a little bit of a long tail to that. There's the potential to put functions to sleep and have them wake up quickly, but some cold starts can take considerably longer than 30 milliseconds to get running. The other bit is 90% of our requests come back within 2.5 seconds, but we want every request to finish so that we can return you complete data. We don't want to miss scanning one particular segment covering a given time range that happens to show, maybe 500,000 requests, right? That'll cause your data to be off by those 500,000 requests. So it turns out functions actually, some of our Lambda invocations never return. You could wait forever and they'd never come back. And they don't necessarily report that they failed until 30 seconds or 60 seconds. So it turns out that there is a useful property here, which is if you're willing to pay for the compute, which we certainly are, if you have 99% of your data that's come in and you're waiting on that last 10%, on that last 1%, retry, right? That you should exercise impatience in order to make sure that you are getting an exhaustive search of your data. Because most of the time, when you have a Lambda worker that fails to come back, it's not that it'll fail to come back if you retry the request, right? It's not a permanent failure that's a property of what you asked for. It's just that the node happens to be busy or unavailable. The other weird thing is Lambda functions are very, very used to either handling HTTP requests or they're used to handling JSON. So if you have data that you would rather send in gRPC format, right, that you'd rather kind of treat more as a protobuf or as a kind of running streaming request, right now, Lambda doesn't support doing that. You have to basically serialize and deserialize the request to JSON, and we've run into fun issues there. Like, it turns out what a surprise. It turns out if you are trying to request, running the same payload against different files, but you're running the same query against, a million different files, if you are serializing that protobuf into JSON a million times, one for each file that you're trying to scan against, that's going to get really expensive. It turns out you might want to cache some of your inputs into JSON because you're doing that conversion. And what happens if you, like us, are trying to return a lot of data? What if you're trying to, for instance, return the number of queries that matched, or sorry, the number of rows that matched a given query broken down by user ID? You might potentially have millions of different user IDs, and the result of that query is going to run more than 6 megabytes. And normally, AWS Lambda expects you to just return in standard out what you want to be returned to the invoke call. But that doesn't really work so well for us. So for larger return values, we actually wind up putting the data into S3 and then returning the link to that, and then we'll read the file out of S3. And finally, let's talk about the cost one last time. Because yes, per CPU second, it's about 3 to 4 times more expensive than EC2. But maybe there's a way to make it cost slightly less. So we keep a pretty good idea of what our customers are costing us, because not necessarily because we're building them for it. In fact, we prefer for our customers not to need to worry about this or worry about the cost of running queries. So we'll eat the cost ourselves. But we still want to know if a customer is running a lot of queries and to see whether we can optimize their use case or to talk to them if they're running, a bunch of programmatic queries that it might be better to scrape with a batch job. So we actually have alerts that are set based off of the total Lambda runtime and the inferred cost in dollars and cents to us per day of that customer continuing to do their workload. But what if those functions could cost less? And what if those functions could also be lighter on the environment to cause less carbon emission because they're consuming less electricity? That would be pretty great, right? So a couple of years ago, Amazon released support for the ARM64 architecture with AWS Lambda. And good news for us, we'd already done the research and done the analysis to make the rest of our workload run on the ARM64 architecture. And I want to emphasize this is not just about the money. This is also about saving our planet. That we can and should try to reduce consumption first, but where we can't reduce consumption, we have an obligation to make it run as efficiently as possible. So these slides are from about a year ago. So about a year ago, Australia was a little bit on fire. And you can see that there are basically these huge climate anomalies, that we have temperatures that are many degrees centigrade higher than they ought to be, that the bush is much drier than it ought to be due to a lack of rainfall, and that's creating bushfires, and that's causing even more carbon to be released, which is exacerbating this cycle. So we have to think about how do we minimize our impact on the environment. And you would say, oh, but we should stop taking airplanes and we should use public transport. But yes, that is true. But we as technologists have a very high leverage role to play here in how we consume software and how we consume hardware. It turns out that a staggeringly large percentage of energy usage is from data centers, is from computation. So the best way for us to help that doesn't involve replacing a whole bunch of cars and, yes, of course, we should replace cars, we should replace airplanes, but we, with just a couple of keystrokes, can actually have a significant impact on the roughly, I think, 3.5 or 4% of emissions that are caused by computing. And no, buying offsets does not work. Buying offsets is, turns out it's pretty fake. It doesn't actually result in meaningful reductions. So let's focus on wasting less power. So think about whether you have to run that workload. If you do have to run that workload, figure out the most carbon efficient place to run it. And This is your obligatory mention by a speaker because every speaker has to talk about AI. And I'm here to tell you not to do AI unless you absolutely have to, because that stuff sucks up a lot of power. So, in that spirit of using less power, let's talk about how this workload, which we think is essential, right? Like, it's essential to help people be able to debug their software when it's failing, right? Failing software can cause user inconvenience. It can even cost lives. So how do we cause software failures to take less time to resolve? Well, we have to have observability, so it makes sense to continue to run this workload. So in 2021, in 2020, we had the opportunity to trial Amazon's new Graviton 2 instances. And those instances, we found, required some adaptation to software to make them work correctly. But when we did that adaptation, we were able to see roughly 30% performance gain per instance. And those instances also cost about 10% less per instance. So that was a pretty big win for us. What adaptation did it take to migrate to the ARM architecture with our server full applications first? Well, we needed to make sure that our base images and tooling could be built for ARM64. And we needed to check to make sure that all of those auditing and logging and those operating system level constructs were there to satisfy compliance. And we also had to check over all of our code to make sure there wasn't any handwritten assembly code in there that was going to cause our applications to not work at all. And finally, we had to change our CI tooling in order to produce different artifacts. Because the ARM64 architecture cannot just run a x86 binary in place, you have to compile something in order to use the ARM64 instruction set. But the good news is, with our build tooling, we are able to template our builds and pass a single different environment variable to our build system, and that causes the Go language compiler to automatically generate a cross-compiled binary for ARM64. So we didn't really need to change our entire infrastructure. We just needed to have it produce a second artifact built with a different environment variable, similar to how you might have optimized and debug binaries, and to store that new artifact in a different place so that we could refer to either the ARM64 or x86 binary. Guess what? If you are using a language that uses a runtime like Java or Python or the JVM ecosystem in general, you don't have to lift a finger. Things should mostly just work, with a caveat that JNI libraries might require making sure that you have the correct multi-arc JNI jar. C++ with hand assembly, maybe don't use that as your first foray into this field. So I would stick to Java, Python, .NET, or Golang for any initial experiments with ARM64. But we did it. We had a working binary. Now what? Well, it turns out that actually validating and rolling it out and verifying that you get the performance impacts that I'm telling you up on stage, every workload is different. Your workload, right? Like this is like, previous performance is not indicative of future financial results, right? Or, talk to your doctor about whether this is right for you, right? Like, so just because I saw 30% to 50% price performance gain does not mean you will. So how do we actually validate this and make the case that it is worthwhile switching? So what we wound up doing was we wound up using that wonderful infrastructure that our platform engineering team had built around continuous integration, around GitOps, around Terraform, in order to be able to run a controlled experiment to trial having one of our workers out of 30 running the new binary just to verify, does it work at all? And then after we did verify that, we also wanted to make sure that we had the telemetry, right? We wanted to make sure that we could compare and contrast the performance of ARM64 versus x86. But because we dog food, it's relatively easy for us to say, okay, I'm already using Honeycomb or any OpenTelemetry compatible thing really. Add a new attribute, right? Add a new attribute to all the trace commands that are being emitted that says which architecture did you run on. So once we had the data, then we could start bumping up to 20% to get a statistically significant sample. And we could see, okay, does this perform better? And it did. So we went ahead and we hit the switch. And we said, we are going to migrate this prod workload as soon as Amazon declares its instance type generally available. So we did. and we're migrating from spot instances to on-demand ARM instances, and then we migrated from on-demand ARM instances to spot ARM instances as soon as they became available. And you can see that the drop in price is pretty significant. And this drop in price comes from several factors, right? Number one, it turns out that by just squeezing the instances down and running 30% fewer instances, we're able to, achieve significant cost savings from that, and also each instance was cheaper on a per instance basis. So that's well and good, but can you do that to other services, right? What about the stateful ones that are actually storing that data, the ones that are writing to local SSD? In that particular case, we were using a particularly ancient SSD attached storage version of the it was the i3 series on Amazon, and in this case we were not trying to make it cost less, we were trying to make it perform more. And by migrating to instance types that were better suited for a workload, that were much more performant per core, had twice as many cores, and also had slightly less solid state storage per instance, but that was fine because we had started tiering since we originally picked the i3 instance type. So basically, we chose to pay about 10% more per machine and got about a 3x performance improvement by kind of more fine-tuning our performance characteristics and getting the most modern CPUs. And this headroom really, really helped us, because previously we were bumping up against the capacity limits of those instances. Here's a side note, by the way. Why is it that ARM64 performs about 30% better per core? It actually isn't necessarily 30% better performance per core. It's 30% better performance per marketed vCPU. So the secret with Intel and AMD processors is that they are hyper-threading, right? When you buy 2 vCPU, that's actually 2 instruction decode units, and it's 1 actual processing and compute execution unit. What's happening is Amazon and other providers are selling you those 2 instruction decode units that, if you're running the same workload, you're contending yourself for that actual execution. Whereas with ARM, there's no hyperthreading. 1 vCPU equals 1 dedicated core with both decode and compute. And that means that as you are starting to saturate the instance, you're not contending yourself, and your tail latency doesn't spike until the CPU saturation really gets above 90%. Whereas an Intel instance or an AMD instance with hyperthreading is going to wind up saturating its CPU when you start running it overall at about 65 or 70% CPU utilization, because at that point, the instruction decode units still have plenty of headroom, but the actual compute unit within the core is fully saturated. So when we actually switched over from the i3 instance type to the M6GD instance type, with twice as many cores, each core about 50% more efficient, we were basically able to keep our instance count the same as we rode out about a 3x growth year on year, which was pretty cool. And then, yeah, we had to horizontally scale out our fleet. But it doesn't just stop there, because it turns out that while we were in the background migrating from 5th generation Intel to 6th generation ARM64 instances, Amazon was busy working on their 7th generation ARM64 instances. And this is a little bit unheard of in the Intel world, where, basically if you get 10 or 20% improvement generation over generation, you're like, yay, this is awesome. But Amazon gave us, just for free, just by incrementing that M6G to M7G, we got a 30 to 40% improvement in performance and throughput by just changing from Graviton 2 to Graviton 3. And we saw the latency was slightly better, about 10 or 20% better latency, in addition to running 30% fewer instances. And as you can see, that really adds up to a lot of savings, because we're able to process the same number of requests and to verify that what's the pod CPU, how hot can I run this, and is everything going according to plan. So over the course of about a year and a half, we were able to migrate all of our x86 workloads, all of our serverful x86 workloads, onto serverful ARM64. And we turned off the last instance of x86 in March of 2022. So observability really helped us kind of dial in on what was going on with our performance. But until Amazon released ARM64 support for Lambda, we didn't really have a solution for converting over our serverless functions. But when they did have it ready, we were eager to adopt it. And we tried it because, hey, why not? Free performance, right? Like it makes everything 30% better. It's magic, right? And then we A/B tested it at 50%, and it broke. Why is that? Well, before we started worrying about why is that, we needed to first figure out, okay, how do I revert this, right? How do I restore performance back to normal? Good thing was I'd thought ahead, and I'd implemented it as a feature flag. So I was able to, in less than about 30 seconds, I was able to switch that feature off and restore state to normal so that I could start unpacking and debugging and figure out what had gone wrong. So what had gone wrong? It turns out that continuous profiling is hugely useful for getting to the bottom of things like this. But in short, one of the libraries that we were using for compression, because it turns out you don't want to store large strings that are basically the same string over and over and over again. You don't want to store those and compress. You want to compress them first. So we use LZ4. And the LZ4 library in Go had hand-implemented assembly for x86 only. It had a fallback implementation for ARM, but the fallback implementation for ARM was not that good. So we had to port the ARM32 implementation to ARM64, and then it just magically worked and got faster. And also, it turns out, when Amazon releases a new instance type, when Amazon releases a new feature for Amazon Lambda, like running on a new backend, if you suddenly scale from 0 to 100% or 0 to 50% without any warning to Amazon, and you're a significant user of that service, you're going to wind up getting throttled because servers are not magic. They don't pop out of nowhere. They need to be provisioned by Amazon. And this is one case where, it's actually bare metal servers all the way down. That actually does apply. You can run your provider out of capacity, especially if it is the day after they've launched a new instance type. So, we went back and talked to Amazon and said, we'd like this many instances. And they said, give us a second. How about you continue to run, 50% or 30% on x86 for now, and we'll give you those ARM servers as soon as we can. And the last thing was until Go 1.18, there was no support for the register calling convention for Go on ARM64, which meant that the Intel instances had a significant advantage over the x86 instances because Go had not yet implemented the register calling convention for one of them, but not the other. It turns out passing each function call argument into the stack is a little bit expensive. So that's all fixed now. Those are things you don't need to worry about. But the important thing is being able to debug them, right? Being able to figure out where is this performance regression coming from, because it is a new architecture. It is something that your software may not have been tested against, so it's important to be able to measure and optimize and debug. So after we figured out what was going on, we were able to flag it from 0% to 1% to 5% to 10%, and working with Amazon, we were able to scale up to 99%. Why not 100%? Because we want to be sure that we can continue to run this workload on x86 just in case. So that's what that looks like, right? That's the adoption curve of going from 0% to 100% ARM on the serverless side. Is a lot of thoughtful experimentation, a lot of capacity planning, and a fair bit of performance engineering, with the result that 3 to 4 times as expensive per CPU second, that's less of a worry for us now because we've been able to benefit from that 30% performance improvement from running ARM versus x86. And this is what it looks like in practice. The latency is about comparable. And the reason that the latency is about comparable is that I've taken each Lambda worker that would have been running on x86, and I've shrunk the CPU and memory by 30%. So that's why the latency looks like it's indistinguishable. It turns out that I'm cheating a little bit by just running smaller workers. So my message to you is, yes, do this at home with a couple of caveats. First of all, if you're going to use serverless functions to use as the backend of your real-time database, you're going to need to first move that state from local machines into object storage so that serverless functions can even query it in the first place. To generate lists of objects and to generate kind of work units, you don't want to process one file or one segment per Lambda. You might want to process like a batch of 8 or 10 of them. That way the startup cost and the invoke cost is amortized. You can use the serverless functions to beautifully parallelize object processing, although, as I said, be wary of the generation of the invokes. Make sure that you've profiled that is as quick as you can make it. And then finally, you may need to reduce the results outside of Lambda afterwards and kind of merge those tens of thousands of workers, those potentially hundreds of thousands or millions of invoke requests. When the result comes back, you're probably going to want to merge it together into a single result. But where are the dragons? If you have latency-insensitive batch workloads, those are better suited for EC2 instances, right? Like you can run those with AWS Spot. You can kind of save and resume them. You can tolerate the 2 to 3 minute startup time of a EC2 instance. So why run it on Lambda and return a result within seconds that you're paying 3 to 4 times as much for, when you could just wait for an instance to spin up, as long as you're willing to wait potentially minutes or hours for the result? As I was saying, don't send only 1 or 2 files to scan to a Lambda. They have a large startup time. In particular, one of the things that we found is that our workers, until we pre-cached the SSL certificate validation, our workers were spending something like 5% of their time just handshaking with S3 over HTTPS. So you kind of want to start with kind of these larger batches to kind of amortize setup costs, and then see what you can do to reduce those setup costs. And check with your cloud provider, be in sync with your account rep if you're going to do this, state your intentions to them so that they can provision capacity. They're usually more than willing to do so, you just can't turn from 0 to 100% all at once. And finally, even if you're not ready to do this now, you should still future-proof. ARM is here. Your Mac laptops are running a version of the ARM instruction set. So you already need to be testing cross-compilation. So you may as well do it now. Don't assume the whole world runs on x86, because it no longer does. The most cost-efficient processors are going to be ARM. And before you actually scale out fully, right, like make sure that you're tuning the batch size per invoke, make sure that you're running profiling, make sure that you have adequate observability to tell if there's regression per architecture, and measure your metrics carefully and have costs so that you can have an idea of what's going on and which customers' workloads you might want to throttle or move to a different backend. So ARM64 is a huge cost and planet saver. But you really have to think about, okay, what do I need to do to get ready? Well, CI pipelines, multi-arc Kubernetes clusters. I was hugely relieved, actually, that we never had to go through multi-arc Kubernetes, because we migrated from EC2 x86 to EC2 ARM64, and therefore we didn't have a mixture of architectures. But I know that's probably not going to be the reality for most of you, so you may have to experiment with Kubernetes constraints. And then deploy to production and really, really measure the results. Kind of hammer home the cost savings that you're going to get. Because yes, it is slightly more complex to maintain different build architectures, but it's well worth it if you can cut your company's cloud bill by 20 or 30%. And at the end of the day, nothing matters unless users are happy. And in this case, that is a very happy dog. So I'm happy when the dog's happy. If you'd like to learn more about our query backend, you can go and have a look at Observability Engineering. It's being sold in the bookshop, and you can also get a free copy online. And with that, I think that's all that I have for you. Thank you very much.